start off with a basic question that it's already been asked, and a lot of people do ask going into calc. What is it? What is calculus actually? Calc is really just math in motion. I know that's a really pathy way of describing it because it doesn't really tell you anything. It doesn't have an intuitive meaning. What that means is that in the past, when talking about a math problem, we might have something like solve for this intersection, right? Find this point right here, give me the XY point. That's all well and good. But all we're doing here is setting two things equal and solving it. And that's actually what a lot of this section is going to be about, or part of this section. But what about how to describe something like this? So let's say this is a function, right? And we want to know what y value associates with this hole in our function. We don't really have any tools from algebra to handle that because our function just doesn't exist there. We would put in c and out would come nothing. Maybe this is something like, a really good example would be this is the function f of x is equal to x plus 2x minus 2 divided by x minus 2. This has a hole here. And this would be y is equal to 4. How do we solve something like this? Where we want to say, when we get close to 2, what does our function get close to? This is a lot of the stuff that calculus is concerned with. When we get close to a value, what does our answer get close to? And the way it goes about this is using what's called a limit, which we should be able to see by the end of this class. But having said that, calculus, like I said, is really about math in motion. When you get close to a thing, what happens? But what that leads to is other questions like, well, to start off with, we know the slope of this function, right? Pretty straightforward to find. This is mx plus b is equal to y. The slope is equal to n. But what about something like this? Let's say I wanted to find the slope here. How would I do that? Well, one thing we could do is take a secant line and squeeze these 2 points in until they get to that spot. And say, all right, the slope of that tangent line then is the slope of our graph of our function at that point. This is what's going to be called the derivative. You can think of it for right now in an intuitive way as the slope at a point. But it also leads to another question, or answers other questions, like to give the first example, let's say we've got a line and we want to know this area. Well, that's pretty straightforward because this is just a triangle inside, right? And we know how to find the area of a triangle. But what about something like parabola? How would you find the area underneath that? Well, algebra doesn't give us a good way of figuring this out. We can approximate it. We could take a bunch of rectangles and make those rectangles smaller and smaller and smaller, find the area under each rectangle or of each rectangle, add that area up, and as our rectangles get smaller, they'll get closer and closer to an approximation of what that area is underneath our parabola. To do that requires what's called the limit. So the limit shows up in answering that question of what's this hole at? What's the XY position of our hole in our function? It gives us a way of finding the slope at a point on our function and a way of finding the area underneath our function between some X values. But also something that shows up because of this relationship with the limit is that the area underneath our function is also going to be related to the slope of our function. So this idea of math in motion it really comes up from this idea of the limit, where the limit is going to tell you when you get close to a thing, not what happens at the thing, because you might not have an answer, but when you get close to that thing, what happens? So it changes our thinking a little bit from what we see in algebra. Having said all of that, let's get into the actual lecture. Where is full page? Right there. So, some basic review. Just the anatomy of the Cartesian plane. We have our four quadrants. We have our origin. Origin's obviously at the center of the graph, right? This is going to correspond to the point 0, 0. Our quadrants, they end at our axes, right? So everything between our axes we say is a quadrant. Everything on our axis is just on our axes. So the next question then is, how do we use it? Well, what the Cartesian plane allows us to do is to set up a relationship between the x-axis, the y-axis, and a point, right? Just taking two number lines, crisscrossing them, and saying, if we move in a particular direction relative to each of the axes, then every point along that particular line is going to correspond to the same x or y value. So here might be y is equal to 4. And here might be x is equal to 2. So this point would correspond to 2, 4. And every point along this purple line will correspond to some x value, 4. And every point along the red will correspond to 2 and some y value, right? So in that way, what we really have is that a single point is just the corresponding x, y value. Yeah. Like I said, nothing revelatory here. So to plot a point, say -1, 2, we'd want to go to -1 in our x direction and go up 2 in our y direction. We plot that point accordingly. Make sense? So mathematicians are nothing if not particular about naming everything. We like to categorize whatever we can. And whenever we have data like this that we plot, it's called a scatter plot. It's just a bunch of points. For anyone who has ever shot a shotgun, think of it like bird shot. Just a bunch of points, right? That is a scatter plot. So if we're given, say, something like this data here, where one axis represents time and the other one represents amount. So this is the amount spent on snowmobiles relative to time. We would say one axis is going to be t, the other is going to be a. Typically, we would say that x-axis is t, and the y-axis represents a. And we'd go through and say, all right, at 1997, the amount is 1006. Plot a point at 1997, 106. Yeah. So when we do that, we get this nice, lovely scatter plot. But notice down here, we have this zigzag. This zigzag is basically the mathematician's way of being lazy to say, I don't want to write every number from 0 to 1997. So I'm going to skip a bunch. That's all we're saying there. So if you were ever to ask to draw a graph like this, you could just go ahead and say, skip a bunch, go to my first value. Yeah. And we could do that in both directions, x or y. in the positive or in the negative direction. That zigzag is just a way of saying, I'm lazy. I don't want to write out a bunch of values that have no bearing on the data. Having said that, we could have also shown the data using bar graphs or with a line graph. So the next obvious question then is, okay, let's say I have 2 points. How far apart are they? I mean, it's pretty obvious if what we have are 2 points, something like 2, 4, 2, 1, right? The distance between these two would just be 3, right? But if they're diagonal from each other, it's not quite as obvious. At least not until we remember the Pythagorean theorem. So what's happening, draw all of this out. Might actually be getting ahead of my notes here. What's actually happening is we're pulling out this triangle and solving for the hypotenuse, the length of the hypotenuse. So what we've got is looking at this triangle being pulled out, right? It's a right angle triangle, so we can just apply the Pythagorean theorem, right? The first thing we need to do is identify the length of our edges. Well, this length is going to be the absolute value of y2 minus y1. And this length is going to be the absolute value of x2 minus x1. So then, let's call this A. Let's call this B. We know from the Pythagorean theorem, c squared is equal to a squared plus b squared. So we can solve for that length, right? And that's what we're going to be doing here. Start by, like I said, recalling the Pythagorean theorem. We say, all right, well, if Pythagorean theorem tells us that a squared is equal to, c squared is equal to a squared plus b squared, then since a is equal to the absolute value of x2 minus x1, and b is equal to the absolute value of y2 minus y1, then c squared equal to a squared plus b squared has to be equal to the absolute value of of x2 minus x1, that quantity squared, plus y2 minus y1, that quantity squared. So all we're doing here is we're saying, all right, let's pull out our graph for a second. Let's just identify the important information. So we pull out our graph and we say, all right, this length is B, this length is A. We happen to know that that's equal to the difference in our X or our Y values accordingly. We want to find this length, right, up here, which is going to correspond to our hypotenuse in this triangle. So we know this hypotenuse is going to have a length of C squared, which is equal to A squared plus B squared. We just defined what A and B were. So that let us get to this point, right? So solving all of this now, this tells us that the distance D is equal to the square root of x2 minus x1, that quantity squared, plus y2 minus y1, this quantity squared. All right, now a bunch of things are actually happening here all at once. One, I dropped the absolute value signs. Why is that? Right, because I squared them. What we're doing is taking the difference of real numbers, right? Which will give us a real number. Any real number squared will always be positive, which is what this absolute value sign was doing for us, right? It's just making things positive. So squaring a positive doesn't change anything. But even without those absolute value signs, squaring was just still going to give us a positive. Make sense what I mean? Mm-hmm. So I dropped those. Now, there's something else that's happening here in the notation that I haven't quite explained yet. The subscripts, y2, y1, x2, x1. What is that?
It's just defining where they are.
Exactly. It's just naming them, right? This idea of x1 versus x2. I don't want to write x for every x value. I want to be able to identify them. So we're using subscripts. Also, we did the same thing here when we were naming B, when we were naming A. We just used shorthand, right? So all this A, B, C, all it's doing is acting like a name that is much shorter than what it's representing, right? Because if I had to write this every time, it would suck. But if I come up with some shorthand, I can save myself some time and some space. So we're really not doing a whole lot of calculation here, right? We're just renaming things and reorganizing them so that it's nice to work with. Make sense? So I point all of that out because this looks a lot more intimidating. But this is exactly what we just did over here. We squared the D. We said, all right, D squared is equal to A squared plus B squared. But then that means D is equal to the square root of the quantity A squared plus B squared. But these absolute values, since we're squaring the quantity and they're just real numbers, they don't really do anything for us. So why don't we throw them out? Make sense? We call this the distance formula. This quantity here, this formula, it's called the distance formula. So if we wanted to find the distance between two sets of points, we just apply it, right? We would decide which is our x1s and y1s, which ones are our x2s, y2s. So question, does the order matter then? Does it matter which one of these I determine to be x1, y1? What I'm asking is, is that going to change our answer? No.
Yeah.
No, well, let's see why. Let's go back to what we had. If we change the order, all we'll do is have the sign flipped on us, right? So if, let's say, for example, we said that x1, y1 is -2, 1. Man, this is gonna suck without AC. I am melting up here. Then x2 minus x1, that's going to be 3 minus -2, which is just 5, right? Now, if we swap that out, then x2 minus x1 will be -2 minus 3, which is equal to -5. So if we look back at our distance formula, we're going to have to square 5 and square -5.
Because you square it, it takes it away.
Exactly. The square of 5 and the square of -5 will be the exact same, right? So it doesn't matter which order we dictate our x2, y2s, x1, y1s. That said, it does kind of make sense to go ahead and say this is x1, y1, right? Just because it's to the left. And since we live in a Western nation, reading English, we read it left to right, makes sense to us, right? To go ahead and say 1 comes before 2, left to right. Here's a curious question I forgot to ask in Arabic. Are graphs flipped? I doubt they are. So, going through the solution, we would just identify our x1 and our x2, y1, y2, and throw it through the formula. So a natural question would occur insofar as homework is concerned. Which answer do I want? I would say don't give decimals. If it doesn't ask you to give a decimal, don't give a decimal value. The square root of 34 is the answer. 5.83 is not. It's an approximation of the answer, right? That said, WebAssign oftentimes will say, round it to the second decimal. In that case, go ahead and round it to the second decimal. But if it's me, stick with square root of 34. Because we might have later down the road, I ask you to do something with that, it would be convenient to have it, right? Like, what's the distance squared? 5.83 squared is not obvious. Square root of 34 squared is, right? So for that reason, I would suggest avoiding writing decimals when you can,
For tests though, we're probably gonna have to do since it's online.
more often than not, yes. So, let's say we're given a triangle now. Triangle has 3 points. So it's going to look something like this. How are you going to find all these limits? Well, because this is a right angle triangle, if you just found D1 and D2, you could go ahead and apply the Pythagorean theorem straight to D3, right? Or you could use the distance formula to find all 3. So there's 2 different ways of going about this. Make sense what I mean? What I am saying is, in our case, we've got, make sure this is good and big so everyone at home can see it. Point x1, y1, let's call it 2, 1. x2, y2, let's call it 5, 7. x3, y3, let's call it 4, 0. Well, D1 is going to be the square root of 5 minus 2, that quantity squared, plus 7 minus 1, that quantity squared, right? Which is going to come out to be the square root of 3 squared plus 6 squared, which is going to be 9 plus 36, or the square root of 45. Two is going to be D2, let me mark these so that they're easier to read. D1, so that means these 2 will be D3. All right. So D2 is going to be 4 minus 2, that quantity squared, plus 0 minus 1, that quantity squared, which is 2 squared plus 1 squared, or the square root of 5. Everybody agree? Okay. So now we have a choice of how we're going to solve D3. We could use the same formula to solve D3. Let's do that real quick. D3 is equal to the square root of 4 minus 5, that quantity squared, plus 0 minus 7, that quantity squared, which is equal to the square root of 1 squared plus 7 squared, right? assuming I didn't do anything wrong here. So this is going to be 7 squared is 7, 14, 21, 35, 49. Say what?
No, you want that, sorry.
What's the square root of 7 going to be? 49, right?
7 is 49.
Yeah.
250. That's fine.
All right, so that's the first way we could have gone about it. The claim, however, there's another way. We could have said D1 is equal to A, D2 is equal to B, so D3 is going to be equal to the square root of A squared plus B squared, which is going to be the square root of square root of 45 squared plus square root of 5 squared, or 45 plus 5 square root of 50. This is an example of why I would suggest not writing everything in decimal form right away. Because if we were thinking about this in terms of Pythagorean theorem, this is a lot easier than that, right? That said, pick the path that's easiest for you. This only worked because we had a right triangle. We may not always have a right triangle. We could have picked another point that was slightly off cantered. Let's say 4 was, this was 4 comma negative 1 instead. We wouldn't have been able to apply the Pythagorean theorem here because it only applies to right triangles. So this happens because of a special case. Because A and B are at right angles to each other, right? But if it wasn't the case, we'd have to have gone through that first route. So moral of the story, there may be shorter routes. If you see a shorter route, don't be afraid to take it. But make sure that that route applies. So going through and checking everything, we do in fact find that D1, D2, and D3 are as we defined it here. And they also pointed out the same thing. You could have applied the Pythagorean theorem.
So question.
Yeah.
It's not really a dumb question, but so is distance formula just for right triangles?
No, the distance formula is for any 2 sets of points. The Pythagorean theorem
It's just for right triangles.
is just for right triangles, yes. So this always works. Always, always, always works. Pythagorean theorem only works on right triangles. So having said all of this, what about the midpoint? What is the midpoint? How would you find the midpoint? Let's say we've got 2 points. the midpoint is going to be make this a little bit longer. The midpoint should be right about here. So we're given a point x1, y1. And the point x2, y2. The question here is, the hell is this point? Now, to answer that question, let's start by imagining imaginary lines through this. Lines that are parallel to our axis, right? And let's notice something. That distance is going to be the same. And moreover, these two distances are going to be the same, right? So imagine like this. Pulling this out now, this distance is just going to be y2 minus y1, right? The absolute value. Agreed? Because if these two distances are the same, and we know that here we've got this right triangle, right? Then this leg is going to be the length of that leg, right? Make sense what I mean? So we're splitting this in half, so that must mean automatically, at least, y middle is going to be the distance between our y values divided by 2. Make sense? Playing the same trick, the distance in our x direction, we're going to see the same thing happen. So again, since we're dividing that distance in half, this point has to be x2 minus x1, the absolute value of that, divided by 2. So the midpoint between 2 points is just going to be the average of their x values and their y values. Does that make sense to everyone? So just really quickly defining the idea, it is the average, like I said, of the values at the endpoints. And I have a typo up here. Let's say plus, it is the average. Sorry about that. The distance is, if you want to find the distance between those, you do that. That's typo on my part. So since we're finding the average, X1 plus X2 divided by 2, Y1 plus Y2 divided by 2. Everybody cool with that? So, for the sake of time, what time is it?
7:25.
7:25. Yeah, I'm going to go ahead and skip this example. Find my charger. My laptop is about to die. Sorry about this, everyone. And I'm, like I said, going to skip this problem. Oh, all right.
I have a question real quick.
Yes, ma'am.
On the whiteboard, are those supposed to be pluses next to the graph as well, or are those supposed to be minuses?
These are supposed to be minuses because they're the distances.
Okay,
So what it should be indicating to us is that if we were going to move this to the origin,
mhm,
we would get 0, 0, right?
Yeah.
Which means that moving this to the origin would require us to use a transformation that's halfway between these two. Does that make sense what I mean? And I'll talk a little bit more in just a second about transformations. Actually, I'm going to talk about it right now. Okay, so let's say we wanted to move this so that our midpoint was on the origin. Then what we would want to do is send this point to 0. What this difference is telling us is that all we have to do is use the translation minus this point. And I'll explain all of this in just a second. Because it'll be easier with another example to see this. All right, let's say we have this line 1, 3, 3, 1, right? The midpoint of this line would be 2, 2, right? Now we want to move this line so that the midpoint is at 0, 0. What we're going to do is use the translation what this translation tells us is that every point, the x direction is going to be moved to the left by 2, and the y direction is going to be moved down by 2. So that'll go somewhere like this if I had the ability to draw parallel lines. This would go somewhere over here. So we would have the new line, the new point rather, So what we've done is we've said, we want to take and put this midpoint on the origin. What that means is we need to subtract 2 from our x value, subtract 2 from our y value. That's the same thing as this translation. But if we're going to do it to our midpoint, we need to do it to our endpoints as well. So this is equal to 1, 3 minus 2, 2. One, 3 minus 2, comma 2, which is equal to 1 minus 2, comma 3 minus 2, or negative 1, 1. Does this make sense to everybody?
So for a translation, all you're doing is subtracting the endpoints from the midpoint.
Not entirely. So this is just one example of a translation. If we wanted to move this line, translate it so that the midpoint was on the origin. However, we could do things like try to take this triangle, move it over 2 units and up 3 units. So it's not necessarily something to do with midpoint, but since that last problem, I was trying to explain it without getting into translations, and I think I, no pun intended, got lost in translation a little bit. Wanted to use that example first. So all a translation is you've got a bunch of points. Then you start off with a table. All right, so we start off with a bunch of points. And we said we want to move these points by some translation. We're going to translate them by plus or minus the ordered pair of the point AB. So the first thing we should note is that this is really x1, y1, x whatever, y whatever, right? Now we want to translate them by AB. And this will be y, or my mistake, x1 plus or minus a, y1 plus or minus b, x whatever plus or minus a, comma, y whatever plus or minus b. That's all these translations are doing. So here, we're moving it up or down by B, and left or right by A. Everybody cool with this? Dope. So, jumping ahead, let's talk about graphs. So, I'm gonna say that a lot, so might make that like a question of the week at some point. We might need to talk about that in a little bit. How many times do I say so in a class? Be a good exam question. When talking about trying to sketch a graph, it would help to start off with a table like so. There, went again. And what we're going to do is we're going to say, we've got some x values, and we know y is related to our x values. In this case, 7 minus 3x. Starting off with a bunch of x values, maybe you want to start with 2, -1, 0, 1, and 2. Then we come over. We find out what the y values are. In this case, starting off with -2, we get 6 plus 7, 15. 3 plus 7, 11. 0 is 7. 1 is going to be 4. My mistake. Are these only right just now? 13. Okay. And then 2 is going to be 6, 1. Yeah, I did 2. That's supposed to be 10. That's why it was bothering me. I promise I can do math. All right. From here, we just go ahead and plot our points, right? Our points are going to look something like this. So from here, we're going to say, let's find a curve that's most appropriate to fit our data. In this case, our data looks like a straight line, so we can use a straight line to fit that graph, right? Again, all of this is just really review right now. We're going to start off by just calculating some points. Then we're going to make a scatter plot and find the best fit line. In our case, again, straight line makes sense, so we've got our nice little line graph. Again, nothing revelatory. But then we get to cases like x squared minus 2. We make a table, we plot our points.
No correlation.
Say what?
There's no line.
Yeah, it's not a straight line, certainly. Instead, it's a parabola. The best fit line is the curved parabola. And this method pretty much works for everything we're going to do in this class. If you need to draw a graph by hand, start off by making a table, plotting the points, and then finding the best fit line. Having said that, there are a couple things that are going to be helpful when plotting these things. The X and Y intercept. The X-intercept is when we intersect the X-axis. So we set Y equal to 0 and we solve for X. And the Y-intercept is going to be when our graph crosses the Y-axis. So we set X equal to 0 and solve for Y. What intercepts look like? We have a Y-intercept, we have 3 X-intercepts and 1 Y-intercept at the origin, 2 Ys, 1 X, and then in the case of the circle, we don't have an intercept for that particular circle. So to explain why we set X equal to 0 when we're solving for Y-intercepts, check out what happens when we pass the Y-axis. X has to be 0, right? So that's why we're setting it equals X equals 0. So to show what I mean, set X equal to 0. And in the case of X-intercepts, excuse me. So a Y-intercept is going to have coordinates of the value zero some Y, right? An X-intercept is going to have the values X comma 0. So this gives us some insight into why we're setting Y or X equal to 0 and solving for the other. Since we have to go through the Y-axis, X has to be 0 to find out what that Y value is. Since we have to go through the X-axis, Y has to be 0 so we can find out what that X value is. So as 2 examples, let's say we want to look at A. Y is equal to X cubed minus 4X. The first thing we might notice is that we can pull out an X, right? So let's factor out that X. Okay, well, X squared minus 4, that's of a particular form, isn't it? That's of the form A squared minus B squared. And from algebra, we should recognize that this is going to be equal to A plus B times A minus B, right? So if that's the case, then we can factor this out further as X times the quantity X minus 2 times the quantity X plus 2. Okay, I did this for a very particular reason. It's gonna make it easier for us to solve when x is equal to 0, right? 1, because when x is equal to 0, we're multiplying all of it by 0. Yeah, so it's got to be 0. So it doesn't matter what these two come out to be. We're already going to get 0. So this gives us that our y-intercept is going to be at the origin. And so, in the words of somebody cooler than me, fucking dope. Now, the x-intercept, we want to set y equal to 0. So what we're doing then is saying x times x minus 2 times x plus 2 is equal to 0. We've got 3 different things that could be 0 here, right? In order for this to come out to be 0, one of these will have to be 0. When x is 0, everything else is 0. So automatically, we know one case. When x minus 2 is 0, is the other case. And then the third case is when x plus 2 is 0. We have to solve all 3 cases, right? So, solving all 3 cases, the first one is straightforward, x is equal to 0. Adding 2 to both sides, x is equal to 2. And subtracting 2 from both sides, x is equal to negative 2, right? So what we just found then is that our x-intercepts are the points 0, 0, 2, 0, and negative 2, 0. And that's all she wrote. Notice what these points correspond to is 0, 0 is the only time we go through both the x and the y-axis. And then the other 3 points, all 3 points correspond with an x-intercept. We can see it crossing the x-axis. So, having said all of this, since I see a lot of yawning, let's go ahead and take a break. Stretch your legs a little bit. Figure out how to fix that vending machine.